Okay, cool. Actually, could you zoom back out, please, Patrick, so we can see most of it? I think it should be readable, pretty much the whole thing. I can certainly read it still. If anyone can't read it, let me know. We're right. That's fine. That's good. Okay, so can you see my pointer on the screen there?
Yeah.
Very good.
Okay, good. Right. So I came to a realization that there's two main cycles in NARS. There's the input cycle, and then there's the inference cycle, and they're not actually the same. They are two separate cycles, although we always talk about them as the inference cycle. They're actually two cycles, and this represents that. And I say they're two cycles because the simplistic drawing misses out the fact that we're actually cycling around all the content of the task buffer before we move on to the inference step. And I've kind of captured that here, that there's the task buffer processing is one cycle and the general inference step is another cycle.
Sorry.
So
sorry, are you pointing at things right now? Because I can't.
No,
see
I'm not yet.
Okay.
I'm just explaining the philosophy.
All right. Sorry.
Yeah, that's fine. Now the other thing, this is an actor model, and every box on here, other than the big one that says concepts, is an actor. The big one that says concepts, within that, each of the smaller boxes represents a concept and is in fact an actor. But there is no container around those actors. It's just there to abstract them away from the rest of the diagram. So in fact, there would be a million concepts in that space, all with unique concept names that you can refer to as a term name, just to clarify the way this diagram works. So we begin at the top. My pointer now should be showing NARS's input.
Yep.
So this is our traditional input. We have NARS's input, goes through what I call a sentence parser, and it is a sentence parser as opposed to a task parser, and that will become clear in a minute. Then we have some perception channels, A, B, and C, which feed into what I'm calling for now a cross-modal integrator, which basically outputs a statement, which is a concurrent conjunction of those premises. They go into one arm of the task processing, which is the new input task creator. It's distinct from derived task creators. As we've outlined in the paper, it's important that you separate the two so they are distinguishable when it comes to doing local inference. So new input task creator is there. And we have something called a serializer. The serializer essentially puts a unique serial ID onto every task that's created. It either does it with a new input task from there or with a derived task from there. The key thing to understand here is there is no global data. There are no variables outside of these actors. There is nothing that exists at a global level. Everything is contained within the actors. And it's important that there is no global data because it makes the cache work much more efficiently. There's no issues about locking, anything else. Every actor is self-contained and everything it needs to function is contained within it. So there is no global data anywhere. Yeah, this represents the entire system. So this serializer accepts new tasks and derived tasks, and then they get forward onto what I call the task dispatcher. At this point in time, none of these tasks have been given a creation point. A creation time. This system time provider feeds that into the task dispatcher, and the way it does that, it basically you can set the resolution you want, but for argument's sake, let's say we have a cycle time of 15 milliseconds. So every 15 milliseconds, the cycle will get updated within task dispatcher as representing the system time. Okay, so any task that comes through will be time stamped with whatever the cycle time is. So that will be its creation time. Now some tasks are going to come in here and there won't be any concepts. So if a task dispatcher checks for the concept and it doesn't exist, it then sends the task to concept creator. Concept creator is responsible for creating the concepts, and any subterm concepts related to that concept, complete with task propagation. Yeah, and what it does then? No, you don't need that. You don't need that. No, not necessary. Because it knows the concept doesn't exist because okay, I understand what. Right, so the way it's a recursive process. What happens here, right? So that the task gets sent to concept creator. It creates the first layer of the first level of concepts. It then sends the message back to task creator, having already said I've created level 1. The task creator, the task dispatcher then checks do the level 2 concepts exist. If they do, then it carries on. But if they don't, it sends a task back to concept creator saying, okay, you need to create level 2 concepts now for that task as well.
How does it check, how does it check if the concepts exist or not? There needs to be some message passing between the concepts and the task dispatcher.
Right. Okay. So concepts are actors, and actors have a registration capability, and you just basically you register the concept's term name as a symbol, and then you register the actor with that as a symbol. So all you have to do is literally read the term. Does that? And then you say, does that exist as an actor? And if it does, then it's there. And if it doesn't, you create it. Okay?
Yeah.
All right. All right. So that kind of recursively processes that. There's another aspect of this which is important in the sense that a task could come in that has already been sent to concept creator, but the concept hasn't yet been created. So what it does, it just sends it again. And then concept creator does a quick check to see if that concept does in fact exist or not, and he won't do it again. So there's kind of a little optimization there. Because one of the issues you have is that this is a continuous model.
But what I don't see, this concept creator has somehow to feed in his concepts into this area, so that the task dispatcher does this.
No, this is message flow. When you create a concept, it just appears in memory. You don't need to create a connection to it. So when concept creator says create actor, it will just appear in this box abstractly. Yeah, it will just be, it'll exist as a concept. Yeah, it doesn't need to be connected to anything because you know its name. Yeah, and you can refer to it by its term name.
So the task dispatcher checks whether a concept exists. If it doesn't, it passes a message over to the concept creator, and then it just forgets about it until the concept creator then sends a message back to the task dispatcher after creating the concepts that it's required.
So it basically just sends the same task back. At the simplest level, it just sends the task back, and now the concept does exist because it's created it. And now it can dispatch it to the relevant concept. But you have to remember there's a recursive element of this to capture the subterm concepts as well. So hence that's why it's a circular process. So it creates the subterms if they don't exist as well. But in a loop. So it's a recursive process as opposed to because there's a couple of ways we can do this. We probably don't need to get stuck on the detail here. The key thing is that the concept creator and the task dispatcher between them will ensure that the concepts and all the sub-concepts exist and the task has been propagated to the relevant concept.
Yeah.
Okay. But there's several ways we can do that.
But the propagation shouldn't happen at creation already.
Yeah, it can though. There's no reason why it can't.
This is true.
Exactly. That's what I thought. I know it doesn't do that at the moment. And I thought about this. And I thought, well, actually, this is the place to do it because it's going to happen at some point. Might as well just do it.
Yeah, I agree.
So it's kind of clean and easy, and it fits in the scheme then. So then we've got a task and we've got an existing concept, and then basically a task dispatcher sends a task to the relevant concept. And that will in fact be several messages because a task will be split down to each of its subtasks as well as subterm tasks. So that task will go to all of the relevant terms. Is that clear? Okay.
Yes, but I'm concerned that the task is too much present in the neighborhood of the concept that
Sorry, say that again.
It might cause a control-related issue, but probably not.
I don't think so, but we'll maybe identify some of these problems. This is why I want to talk this through. Okay, so now we're at the stage now where the concept is essentially going to do local inference. And the concept themselves, they're responsible for three things: local inference, general inference, which I'll talk about in a second, and updating of budget. Plus, obviously, all the associated housekeeping, like forgetting and stuff related to that. Now, the second loop, which begins over here, the inference cycle clock. There's no reason why this can't run at a different speed to the system time provider. They can run at different times. So what happens here essentially is there's a cycle of inference, and the way this works is that when a concept receives the tasks or budget update information, at some point they hit a threshold which we'll say is the activation. So that concept becomes active and is available for inference. When it becomes active, it sends a message to the concept collator. And this basically collects every cycle. It receives all the concepts that say they're active. And at the end of that cycle, it then picks n concepts from that list to do inference on. And n can be 1 or 100 or whatever number you want it to be. And what happens then is it sends an inference request to the concept and says, I want to do inference on you. And then the concept is responsible for selecting the task link and the term link. It then sends that package to the concept that the term link refers to as a message. When it's received by the target concept, it will only process that package if that concept is also active.
Okay.
Yeah. Otherwise, I mean, okay. I think that makes sense. It doesn't have to be that way, but that's my current thinking. And then if it's not active, it just ignores it. I mean, we may want to do something with it to modify budget or something, but for now, I'm assuming it just ignores it and it doesn't do anything. So then the inference package is, if it is an active concept, it pulls a relevant belief after it's ranked the belief tables, and then it sends that package to the general inferencer, which does the inference. Now, Jared mentioned earlier, said, well, that's kind of going to be a bit of a bottleneck. But what you can in fact do is you can clone this into multiple versions, and you can route the messages with a load balancing algorithm, so that you can use several inferences if the volume's a problem. But let's keep it simple for now and assume there's just a single general inferencer. It receives an inference request package, it does the inference, and then that sends the results back to the derived task creator. The only other factor to take into account here is at the end of every inference cycle, after it's selected the concepts from the active concept collator, it throws that away and then it starts again. So that's a renewable list that it does every cycle. So there is no high level picture. Any questions, observations,
I
issues?
think there should at least be a way for the concept priorities to influence the perception.
Well, I did think about that. See, I mean, this is a very primitive perception. This is not anything. This is basically just sensor outputs. This doesn't do anything about selection. There's nothing going on there except this is just sensor output. It's kind of like the entry level of the system. So the general inference mechanism is responsible for selecting which are the relevant percepts to deal with. Because that is like the lowest level perception it's possible to get. There is nothing you can do to that. You can't influence it in any way. It's output from a sensor. There's nothing else you can do to it.
But I'm wondering if we need channel-related attention control.
Possibly, I don't know. It's kind of early days on that. I mean, there's no reason why you can't pass messages back to the cross-modal integrator. I can't see a need yet. It's possible there might be one, but I don't know what that is, so I haven't put it in. But it's not at all hard to just send a message somewhere. And that's easy. So it's actually very straightforward to modify this, but I've tried to keep it as clean and as simple as possible, and capture everything that we need to.
Yeah, I agree. I mean, I think we agreed before that this 2.0 would be very sort of clean architecture and clean code base, and that this sort of perception attention is more of a research area, as far as I understand at the moment.
I'm not so sure. Because it's to some extent known that concepts need to influence the perception.
Yeah. I agree, absolutely. But the way I think about this is that the control of perception is an operation, right? And that operation is a function, and that function can control the perception channels directly. It doesn't need to be within the control model as such. It's just an operator within a concept. So if you want to actually activate a channel in a certain way, you need to send an operator, or you need to have an operator that executes that. And that's kind of an invisible layer to this model. There will be a connection between operators and aspects of the system, but I haven't shown those because they're kind of inside the actual logic of the beliefs themselves.
Oh, okay.
Does that make sense?
Yeah, this was my only concern.
Okay, cool.
Great.
Well, that was easy then. So I really like working with the actor model because it is so clean and it's so easy to work with. So some key things to understand here is that every actor will maintain its own state. State is immutable. So you essentially you recreate state every time you pass a message through, which sounds expensive, but in reality, in a functional language, it's actually not. It's not expensive at all because most of the stuff is just a duplicate of what you've already got. So it's just a reference. So it's not a problem. Every box will process certain messages, and then those messages will generate an output. Most of these are very straightforward. So, for example, like the sentence parser, it only outputs one thing, which is parse sentences. The cross-modal integrator, certainly at this stage, just outputs a single thing, which is a sentence, which is a concurrent conjunction. New input task creator only outputs a single thing, which is a new input task that requires an ID to be assigned to it. A derived task does the same thing with a derived task. There's a bit of work got to go on in here, obviously, because this takes the results from the inferencer, which will be the parents of the results, and it will have to generate the relevant evidence trails and update the budget information for that task. but then that just gets fed into the serializer. So, and then every task gets a serial ID, which then goes to the task dispatcher. And then either creates concept or uses the existing concept. And the thing about it, this is kind of a fixed time system. It's not variable like the existing system. A cycle in this system will be exactly the same length. It will always be whatever you set the system time interval to be. So if you set it to 15 milliseconds, the cycle time will be 15 milliseconds. What that means in practice is that your temporal window, that for example in humans it's 80 milliseconds. If you have a system time provider of 15 milliseconds, you're going to get something like, what is that? Five cycles of events that could occur within the temporal window duration, for example. So 5 cycles could occur, and it's actually going to be precise. It won't be vague because it's set by a system timer, and it will be every 15 milliseconds. Unlike the current one where the timeline is kind of a bit roughly approximate based on how much work you have to do in every step. This will be absolutely specific. It won't vary. Okay. The inference cycle time, it's an important thing to have because it allows you to control the volume of output. One of the issues you find with actor-based models is that they're continuous models. They're not step-based. So because of the nature of this system, if you fed every task into concepts and then did the inference on it as we do now, you'd end up generating more output than input, and you'd end up with an amplifying loop. So ultimately you'd end up with too much input. You wouldn't be able to deal with it because it's amplificative. Yeah, so you end up with more output than you get with input. So you got massive gain on the system, and it eventually blows up. So you need a way of controlling that, and hence the inference cycle clock can slow down the inference cycle so that you've got sufficient time to process the input that you're generating. So again, it's one of those tuning parameters dependent on the amount of performance the system has. Faster system with more processors can process more. And the same with the number of concepts. It's another tuning parameter. You can have just one concept to test simple models, or you can have n concepts per cycle. And all you have to do is literally change one parameter, and it will suddenly process 100 concepts every cycle instead of one. So to parallelize this, it's as simple as changing one value, and then it's done. There's nothing else to do.
Oh, okay.
And then the other really cool thing about this is the fact that because of the way the actor model works, you can actually distribute this across multiple machines doing absolutely nothing. Because the actor model itself will manage the distribution model. And what essentially happens is an actor's address incorporates the node ID as well of the concept. So in fact, it's actually very straightforward to distribute this across multiple machines if you need to do that.
This is good.
Yeah, but which is a future step, but it's a nice thing to have. So the things that I haven't included in this that are just worth talking about as we've got a few minutes. The actor model includes a different style of programming. It's called the let it crash mentality, which basically means you don't really do checking. The idea is that you don't check stuff, you just let it crash, and it has this concept of supervision. So when something crashes, it basically says I've crashed message to its parent, and the parent has rules about what to do. So depending on how it's crashed, the parent can either say, "Oh, just restart, it's not a problem," or it can say, "Oh, actually, that's quite serious. We'll have to completely refresh you and begin from the start again," or other things. There's various ways of doing this. So there's all sorts of nice abstractions that the actor model has to manage fault tolerance and recovering from error. another really cool feature is it allows hot code swapping. So you can actually swap an agent out for another agent while the system's running. So what you can do is you can basically make code changes on the fly and then just replace it without actually changing the system.
No,
without stopping it. Yeah, it's a brilliant model. I love it because it's so flexible. The one thing I have not done on this model, and I haven't spoken about yet, is a persistence model. There are various ways of doing that, but I think initially I would just go for a manual save capability and just store the concepts to disk. There are more complex systems which allow, if you like, hot persistence, so that it's a bit like a transactional model that you can guarantee that everything that's ever gone through the system is recoverable and stored to disk in real time. But there's a big performance penalty with that. I'm kind of assuming for now that we're okay with just running the system in memory, and then when we want to save it, we just save the concepts to disk, and then reload them the next time. But there's various ways of doing that when things get more complicated. And again, you can easily add that without a huge change. Okay, so I think my biggest concern and question mark for you, Patrick, really is around this concept selection process, where basically we're setting an activation threshold in concepts, and when they hit that, they send a message to say from here to here saying I've been activated, add me to the list, and then that selection process happens once per cycle based on you could either non-deterministically select, or you could just pick the end most active. It depends on the distribution of the values, I guess, and how many we're picking. But there's various ways of doing that. Again, the detail can be decided later. But are you comfortable with that as a general concept?
I would like to have a curve back because this one is very flexible when it comes to trying out different priority to access frequency mappings.
Okay, sorry, you'd like to have a what?
A curve bag.
Okay, but you can't have a curve bag. That's not possible.
Okay.
You can have the same functionality with the collator though. I mean, all a curve bag does, it provides a curve that allows you to select based on access frequency.
Right, to select based on the priority distribution.
Yeah, well that's just a function, and you can select from this list exactly the same way. So that's not a problem. Yeah. I mean, how that list is actually represented, I haven't gone into the detail, but it's just a table, and you can select from it in however many ways you want to. There's all sorts of ways. You can have multiple selection routines for that bag. It's not a problem. Sorry, for that container, we'll call it. It's not a bag, it's a container. It doesn't have to forget anything, remember, because everything gets thrown away every cycle. So there's no need to worry about finding the last entry to forget it, because it's not a problem. You just store all of them, select from the entire list based on whatever selection mechanism you want to use for that cycle, and then you throw it away, and then you build it again the next cycle, which it's not that expensive because there's only going to be a small percentage of the total concepts are going to be active at any one time. So it's actually relatively cheap.
Yeah. And what is with the DOM links and task links? How are they managed?
Well, there aren't any. That's the point. What happens is that within the concept, you have the same concept of a term bag and a term link bag and a task link bag. And in fact, they are bags. They are bags as they are now. That hasn't changed at all. So the inside of a concept is not that different, but they don't actually link to anything. They are just an address of the concept they refer to. So instead of a pointer to a concept, you've got a concept address, which is
it's
the same in principle, absolutely, yeah. The only difference is it's actually the term itself, because the term is actually the name of the concept actor. So you don't need to break it down or anything. It is literally the term that names the concept is the term that names the actor. So when you talk about a term, you're also talking about its associated actor that contains a concept, which is quite nice and easy. Yeah.
And the task links themselves are managed in a curve bag, or?
Yeah. I think the inside of a concept is the same as it is now. There's some messages that determine what. So there's a message that comes in, do local inference. There's a message that comes in, says need to do an inference request. But the content is still the same. There's still a curve bag for term links, for task links, and there's still belief tables. So that hasn't changed at all. This is kind of above that. This is a high level of abstraction.
But I think for the concept itself, we also need a bag, because let's say a new concept comes in and we have to decide which one to kick out.
What, for removing concepts? Good point. You're right. I've forgotten to put that in. We do need a forgetting process, which I forgot to draw the box for that. The forgetting process can run periodically, all right? And it's something that runs as a background task and just runs through the system, and it actually determines which concepts should be thrown away. It doesn't have to run every cycle. It will run when there's memory pressure, right? So it's a bit like a garbage collector in a sense, and it will whatever the criteria you want to use to delete stuff, it will use that. So it's kind of a it's a garbage collector for concepts, and it will decide which ones to throw away. And there's various ways we can do that, and we may want to do it based on the lowest priority, or we may want to do it on activation frequency, or all sorts of possibilities. But whatever the mechanism is, it's just a sweep process that periodically bins a number of concepts. So it doesn't have to happen as a bag. It can happen outside of that. The bag doesn't work in this model. You can't use it as a container. It works within a concept, but you can't use it outside as a general concept, because you have to be able to access each concept individually as a message passing unit, and you can't do that within the bag.
Cool. In this detail, I don't care, but what we need is definitely a way.
Sorry, a way to what?
I will redraw that. For example, if this one is a concept of high priority,
yeah,
that we have such a priority to access frequency mapping, which can be user defined, and which says which concepts how priority influences the frequency the elements are selected. I think this we need.
Okay. My assumption is that determines what activation is. So there's a priority threshold that says when a priority reaches a certain point, that concept becomes active. All right. And when it's active, it goes into the concept collator over here. At that point, you can do whatever you like with it.
I'm not sure if this threshold model works. We've never tried such a thing.
Sorry, say that again, Patrick.
We have never tried a model where concepts are selected according to a threshold. So I'm not sure if this works.
Well, yeah, no, that's not true. You have done, because some of the early models had an activation threshold within the bag.
Yes, but this one was 0.0.1 or something. So
Yeah, I know, but there's no difference really. You're only going to select the concepts that are, well, I suppose there is a difference in that it won't select concepts below the threshold for inference. I don't see that as an issue in any way, shape, or form. I actually see that as a benefit.
No, let me redraw this bigger. Then you see what I mean. Sorry, before I draw it wrong. Should be, of course, that the higher priority gives a higher access frequency. Let's say we have such a thing.
Yeah.
And if we only have a threshold,
yeah,
it would mean that all the elements which are here would be selected for inference.
well, depending, yeah, one side or the other, yeah.
And these ones don't have a chance at all to get selected. In the curveback, it's differently. It's
What,
just...
hang on, whoa. Why don't they have a chance to be selected? Because they're below the threshold, you mean?
Right.
Yeah, I agree, but you could put the threshold. You could put the threshold here if you want. I mean, it's your choice. Personally, I think when they have an activation level that is so low, there's a point where they're just noise that you want to exclude them anyway. So that's a tunable parameter. You can decide where you want to put it. It's one of those things that will determine the volume of concepts that are selectable for inference, right?
Okay. This one I get, and I think this one is defined, but this part can be, this part is okay. But
okay.
But those concepts, why should they all get equally selected?
No, they're not equally selected. That's my point. They are selectable by whatever function you write that goes in the collator, right?
Oh, so I can define.
You can apply the curve in there. Yeah.
Oh, then I'm fine with this.
Great. Okay. Yeah. It doesn't do all of them. It just gives you a list to work with. The assumption is that only a certain subset of concepts at any time will be active, right? And you can decide how big that subset is by changing the activation threshold. And then once you've got that subset of active concepts, you can decide how to select within that subset based on priority.
Oh, this is fun.
Okay, great.
And red. Okay.
Yeah, I don't think there's anything. There's nothing here that you can't do currently. It does everything. It's just in a slightly different way.
I misinterpreted because I thought you want all those concepts which go here to.
Oh no. There's a step that you're going to select from that set what you want to, because you're only going to select n of those, whatever n is. It might only be one, as an example. So you're not going to do all of them. You're just going to select a subset based on a selection function. But that's what I'm saying about it. It's a way of parallelizing very easily. All you do is just make n bigger at that point. But it's unlikely it's going to be every active concept, given the fact we have insufficient knowledge and resources. It's always going to be a subset. And it's possible that in a very simple model that subset might actually equal n, so that in fact it inferences on every active concept. But I think that's an unusual case, and it's not going to be the general rule. But there may be very simple models with very little amount of data where that is the case. But generally, you're going to have a subset that's going to be processed.
Oh, I see.
Okay. Anything from you, Jared? He may have gone.
Oh.
He said he had to go about 12:45, so that's fine.
Oh, yes.
All right. So can I assume that we're going to use this as an architectural model from now on? Okay. I will start working on the detail about the message passing and what it looks like in that case.
I didn't study this in Closure yet. Is this model supported by the libraries? And
the active system exists. I will send you a link. It's a system called Pulsar. It's actually really nice. I read about a lot about it to make sure it does what we need. It's really good. It's built on top of something called Quasar, which is it's a lightweight thread model that runs on top of the JVM. It provides channels and what they call fibers, and it's implemented on top of that. So essentially what it does, it creates a micro threading scheme on top of the Java threading system. So it basically gives each actor gets its own micro stack that's software encoded, and they use instrumentation injection into the JVM to make it all happen. But it's very efficient, really good.
This one sounds familiar. I had a Scala class at university where we were also using a actor library. I'm not sure if it was.
Actually, this is better than the Scala implementation. It doesn't use akka, which is really what Scala is. This is a new abstraction layer on top of the JVM. It's right down to the metal, so it's very, very efficient. I'm really impressed with what they've done, to be honest. I'll send you the links and you can read through it, but it's really good. Moose Boobs pointed me at it because I was kind of the one thing I missed moving to Clojure was the actor model, because I love it as a programming model. And then Moose Boobs pointed me at this, and I thought, oh yes, this is it. This is what I need. So we're set now. And you can see from this diagram that it looks like a block diagram, but in reality, it's the actor model for the system, and that is literally what it looks like when you run it. The only abstraction in there is the concepts, and it's only a tiny abstraction because they all exist as actors, and the messages just go to each individual box as relevant. Everything else just exists literally as an actor, and you write code within it. It's so clean. It's such a clean model.
So this is the only part where we have a variable amount of actors, right?
Where we have what in terms of the number of concepts? Yes, right. Yes. And I mean, it's no problem having 1 million concepts, right? So it's not an issue. You can do that. So there's not a constraint there. And as you say, that's the only place that there's anything that varies. Everything else is a fixed actor. The question mark, we might decide that we want to add in more than one general inferencer, just so that there's a way of distributing the workloads, because it's kind of quite an expensive process. So finding a way of, finding a way is the wrong way of putting it, but we might want to have like 2 or 3 inference engines running just as instances.
Wouldn't we need to have done this entire thing multiple times? Because no. This one can also become a bottleneck.
It's actually really fast creating a concept, creating an actor. They're 400 bytes. It doesn't take much effort to create it. There are some optimizations we can use. One of the examples is that we create actors. So a concept actor is created as if it was atomic, so it doesn't have any tables in it by default, and it only creates the tables when it receives a task that needs them. So that's a simplification, and then its own processing can determine if it needs a belief table, then it just creates them. Yeah. So there would be there'd be a very slight overhead check going forward, like if it exists, then don't do it, sort of thing. But you got to put that check somewhere. You either do it further up or further down. I personally like to put the computation in the units that are spread out rather than put them into a single bottleneck point. So I mean, I've used this task dispatcher concept in my own model. It's not the bottleneck. The bottleneck is the inferencer. I can tell you now where the bottleneck will be. because that's the most computationally intensive piece of the system.
This is true.
Yeah, so we probably need certainly. I mean, one is okay if you have a low number of concepts, and it also if you keep the cycle time low, then it can keep up. But if you want to go faster or use more concepts per cycle, then you need to think about duplicating up on the inferencer. But it's very flexible about how you can tune this. There's lots of ways of modifying it and tweaking it and changing it. But the two key things are the system time provider. So how much work basically is going to get done every cycle. So if you have a long cycle, then it's not going to actually that isn't going to make any difference, because that it's just going to change the occurrence time. So that doesn't really change it. The rate of input of your perception or these is going to determine the flow to here. The other thing that makes a big difference is how many derived tasks you have, and that's directly controllable by the inference cycle clock, plus how many concepts you select for inference. So it's the cycle is controllable in terms of its throughput fairly easily. So it's not problematic. So I learned a lot doing models for Alan and Chris before that in the actor system. This isn't the same as those. This is a much better model than I came up with previously, but my learning experience has let me come up with this. For example, some of the things that I didn't have before was I cheated and I used a global ID generator so that tasks could have, so that you gave tasks unique serial numbers. But that was always a problem, and I hadn't really figured out. So what I have in this system is this serializer that just puts a unique ID. So there's no need for a global ID number. It's just stored within the state of the serializer, and that just increments it for every task that goes through and adds it to the next one. So really simple process. And the same with the cycle time. Before I only had one cycle loop, like the system does at the moment, one main cycle. But that was really problematic because it would generate too many inferences, and then it would start to back everything up. And I had to put all sorts of things in place to stop it. So the realization that in fact there's actually two cycles going on here. There's the task buffer cycle, which runs at one frequency, and then there's the general inference cycle, which can run at another frequency. It doesn't have to run at the same frequency as the task buffer, and that gives you much more control. So I'm really pleased with this diagram, this model. I think it's a leap forward, and it will be really easy to implement.
This is really good because, for example, if this one runs at higher frequency, the inference then the task put into, then it can, for example, create more results and then just select the best ones.
Yeah. You could do this. You could do things like actually have the system time as a longer process, so that a cycle only changes once every 50 milliseconds, and then the inference cycle could occur every 10 milliseconds. So you actually have 10 sub-cycles of inference for every input cycle, just as an example. So that way you kind of have an iterative process on concepts. And as you say, it gives you a different set of options to play with, so that when you get to local inference, you're dealing with a different set of concepts than if you did it the other way around. If this is faster than the inference cycle, then it's a completely different dynamic going on. So there's all sorts of ways of playing with this.
Oh, this is nice.
Okay, I'll flesh out all the messaging detail so that it's kind of more concrete, and put some descriptions around it and explain how it works in some notes. seems like people are generally happy with it, and then we can use that as an approach. But it may well be that we will discover some issues as we go forward. I don't think so, because I've kind of been down this route a few times already, and I think I've kind of uncovered most of them already. But you never know with these things, so we'll see.
Do you think we should post this design already into Google Group, or should we wait some months till we have something working?
Well, we did say we were going to keep our closure model under wraps for now, under the radar. I would like to get a prototype working, I think, before we go public with it.
Okay.
Yeah, I mean, at least see, for example, we can actually run this model as an actor system without actually doing all the work. You can just create message passing stubs in each of the actors. So general inference, you don't have to write the try deriver and the parser. All you have to do is accept a message, put a slight time delay on it, and then just generate a fake output. So you can actually test this model independent of actually writing all of the components directly.
This is nice.
So, yeah, so it's quite a nice easy thing to test, because it's got extremely well defined I/O. Every actor has a very specific set of messages that go in and out, and it can't affect anything else. It's completely it's ring fence for everything else in the system. So all you have to test is the messages that go in, so they give you what you want to come out, and that's kind of it. There's no other testing required. There's nothing else that can happen. There's no side effects. There's no mutable state. There's no locking. There's no contamination of anything else. It's just really clean.
This is true. It's nice. What I see, this I will first clear. This could be combined in a single actor, but probably it's better to keep it separated.
They can't be combined into a single actor. I don't. Well, actually, yeah, they could. You're right. They could be, I suppose. I try to keep it this way because I want to keep the interface as simple. So this only deals with one type of message, which is a derived task message creation. This only deals with new input task creation. And this only deals with adding an ID to tasks, right? That's all it has to do. You could join them together, but then that would have to then be able to handle different message types. Which yeah, exactly. So it's kind of obvious what's going on now, and because the functionality of those two things is very, very different. So derived task creator does something very different to new input task creator. Yeah, this has to take the result of an inference. It has to take the two parent tasks or task and belief. It has to generate new budget values, and then it has to send the task out. Whereas all this one has to do is just add some default values to a task, and then pass it on. So that was kind of my thinking about why I separated them, because they're doing very different things.
The only part in the diagram which is a bit foggy to me is this part.
Yeah, I need to explain that better. What I think I'll do, I'll actually write some more detailed descriptions of what's going on there, so you can see what I'm trying to achieve. One of the things, there's two ways of doing this. One is that just within this box, you just put concept creation as a part of task dispatching, and it does it as a step. If it doesn't exist, it just creates it. So you could do it that way. What I tried to do was break that out to allow the system some more concurrency, so that it would do concept creation as a separate task. It's absolutely no problem having the task dispatcher create a concept if it doesn't exist. So a simplistic model is task dispatcher checks to see the concept exists. If it doesn't, it creates the task and its relevant subterms and puts the appropriate links and everything else in it, and then sends the task to that one it's just created. So that's kind of straightforward, but it becomes a slight bottleneck for the general task flow. So the idea was, if it needs to create the task, then make that responsibility of another actor. But the issue here is that because the system's continuous, you might get two tasks coming in that both need the same concept. So the first one comes in, it says, oh, it doesn't exist, goes to concept creator. But before that's even finished creating the concept, the next one comes in and says, oh, I need that concept, but it's not created yet. So that goes to concept creator as well. So concept creator has to deal with the fact that it may get another message for the same task it's already done, and have to know to ignore that.
Okay. And this one, when it finished to create the concept, then it goes back to the task dispatcher and says,
yeah, it's not the concept that goes back, it's the task that goes back. Because remember, we haven't processed that task yet. We've sent it to concept creator. So the task goes back to task dispatcher and just goes back into the queue again. And then it says, when it gets to the end of the queue, it says, right, is that concept created? It goes, oh, it's there now. Then it just gets processed.
So here only tasks are going which the task dispatcher was not able to handle because the concept was not yet created, right?
Exactly. Absolutely. Yes. Yeah.
Oh, this is nice. This is really nice.
Okay, cool.
This is really nice. And then, and then it fits
then
back into the task dispatcher,
that's right,
because the concept is already created. Wow, this is really nice. Really nice.
Yeah. So when the concept it creates it just basically appears down here. There's no real connection between this and this. It just appears in the system.
Right. Because there is no real back structure or whatever which keeps this actor.
Exactly. They're just kind of free floating in memory. They've just got an address that you can refer to, and there's no container around them. Yeah.
Oh, this is nice.
Yeah, and it's nice for lots of reasons. It makes the cache coherence work really well because they're just small, relatively small units, so they can go into cache and stay there. Unlike, the concept bag for the system can't. It's too big. You can't put the concept bag in cache. It's enormous. So there's always misses and there's always constant swapping in and out. Whereas in this case, concepts are relatively small and they can sit in cache and be there quite happy. So when you've got an active set of concepts, they're going to stay in cache and be much more performant. So that works really well.
Very nice. There's just one thing which could go wrong. What if a concept is forgotten? And this one, the concept creator just created a concept. The concept forgetter deletes the concept, and the concept creator sends back this task. Okay, then the task dispatcher will just see, okay, this concept does still not exist.
It kind of is a loop, but I guess it's kind of dependent on the default value of a concept. I mean, if you're going to set it so that it can be the lowest concept in the system, that's kind of an issue. It's unlikely to be the lowest concept priority. But then I guess it goes back to we haven't decided what the criteria for deleting concepts is at this point. Yeah, that policy we can define ourselves. Remember that concepts aren't forgotten every step. It's a garbage collection process that happens periodically. So because they're not in a bag, there's no way of knowing which one's the lowest one. So what we do is we run a background process that goes through concepts and then determines whatever the criteria is for selecting the lowest one or the one we're going to delete. And we won't just pick one. We'll pick several. So once memory fills up or it hits the limit that we want, we'll say, right, do a background sweep of the concepts. It'll run through all the concepts, collate them over a period of time, and figure out, right, of all these concepts, 1,000 of them are within the garbage collection criteria, and it'll just throw them away. Or it will be right, remove the last 1,000 that fall below a certain threshold, or whatever it is. There's all sorts of ways of dealing with this. So it's not going to be that typically that the concept gets created and then gets deleted. It will be a period of time before that concept gets deleted, if it ever does.
I see. There's another thing. I see that the forgetting can be directly part of the concept actor of a specific one, because it knows all the parameters which are relevant. It has its budget value. So
Actually, yeah, you're right. What you can do is exactly the same thing we do with activation, except we'll do it for forgetting. So if it turns that you send a list of all the concepts that are forgettable to a forgettable concept collator, and then periodically it will forget a percentage of them, like the worst ones. Yeah, something like that. I mean, that would work. Yeah, that actually might be as it was definitely an alternative approach. Yes, okay. That way there's no pressure on the concept itself to delete itself. It just sends a message when it hits a certain threshold to say, I'm currently forgettable. So if the system's under memory pressure, you could forget me if you need to. Yeah, and then periodically the system says, right, I need to forget some stuff now. Right, what's forgettable at the moment? Oh, these things are. Let's forget 100 of those, because then that'll give us enough space. So yeah, that would work. Okay, that would work nicely. Good idea.
Is there any way that the actor management model can actually detect if a concept or a concept actor is not receiving any messages for a certain while and just kill it off?
Not directly, but the concept can.
Okay.
But that's the thing about actors, is that they're their own bosses in many ways. So the thing about it, you can actually say that if an actor hasn't received a message in a certain period of time, what you do is you set timers within the actor itself and say every 100 milliseconds check to see if you've received a message. And if you haven't, you can say, I'm forgettable. I haven't received the message in the last 100 milliseconds. I mean, I know that's kind of a rough example, but you can do that. So then it can post a message, say, I haven't been accessed in 100 milliseconds or whatever the timeline is. And then you can add it to a list of things you want to check. So it's very flexible how you do this stuff. Does that answer your question, Jared?
Oh yeah, absolutely.
Okay, fine.
Okay, then we're finished, I guess.
I think so. Cool. All right, that's great.
Implemented.
Okay, so it's over to you and Razum then, eh?
Off we go.
Okay, guys, I'll write this up in more detail, explain the messages that are passing between units, add some notes, detail what's going on in a concept, a bit more detail. But that's basically what's happening now. So there's not really a change there, just converting it to a message passing format. And I'll get that out, and then we're good to go.
Sounds great.
Okay.
Okay, thanks, guys.
Ciao.
You're welcome. Bye.
Bye.